In this video, we are going to do simple linear regression using SPSS. To do simple linear regression, there are many ways to do it in SPSS. And in Anova lecture, and we talked about using general linear model, univariate approach to do it. And instead, today we are going to use regression linear option. And these two options actually will produce same result. And although the reason we will use this option today is this approach actually do have very useful options automatically to check assumptions of linear regression. So second half of this lecture, we will talk about how to check assumptions. Okay, so let's begin. So we go to regression linear. Independent variable, let me start, reset, and you put the plasma volume and then put the weight under independent box. And let's go ahead to click statistics box, and we want confidence interval. Let's check this is 95%, okay, and continue and okay. That's easy, right? So let's take a look at SPSS output one by one. So first thing, and we probably want to check, is this box, because we are interested in association between body weight and plasma volume, which is shown as this beta coefficient. So this 0.044 provides a slope. What does it mean? There is 0.044 liter increase in plasma volume by body weight increase of 1 kilogram. Okay, and that is statistically significantly different from 0. P-value is less than 0.05. Okay, and this provides a confidence interval. In linear regression, examine absolute difference, absolute change in y by 1 unit increase of x. So the null value, the value indicating there is no association, is 0. So that null value is not within this confidence interval, and therefore that indicate p-value is less than 0.05. Okay, and let's look at this Anova table. Okay, so this Anova table also provide p-value. Okay, in this case, which is the same as 0.029, same as p-value of a body weight. Okay, although it's not always the same. Now what this p-value does is it examines usefulness of this regression, okay? Or we can say global test for this regression model. And when you have more than one independent variables, for example, if you want to adjust patient age and race and sex, and with the body weight, and you have 4 independent variables in the model, and each independent variable produce p-value, or p-value is computed for each independent variable, and therefore, and you have multiplicity issue, right? So more independent variables you include in the model, and chance of detecting at least one independent variable is significantly different increase. So in order to protect you from inflating that type 1 error, and this p-value assess whether all of the effect of all 4 independent variables, okay, effect of all the independent variables included in the model are simultaneously 0 or not. So if you have one very strong independent variable, in that show the significant association, and this p-value will detect that. Okay? So if this p-value is greater than 0.05, and you conclude none of the independent variables show significant association, and therefore you don't even look at p-value of each independent variable. Okay? So if this p-value is not significant, and at least one independent variable is significant, and that's indicate, and you inflated type 1 error, you look too hard, you included too many independent variables, and therefore you are detecting the significance just by noise. Okay, so this p-value, you can see that as a very similar p-value to ANOVA. That's why this table we call the Anova table. Right. And next, the model summary table provide R square. So this value is R square. So, so we can say there is 58% in plasma volume. Okay, 58% of variation existing in plasma volume is explained by body weight. Okay? So higher this number is better, but it won't exceed 100%. And if you take square root of R square, it gives R, which is 0.759. And if you redo Pearson correlation, and then Pearson correlation value would be the same, would be this value. Okay? Except when this could be negative. So negative times negative would be positive. So you can't really see if the association of negative or positive just by taking square root of R square. So for that one, and you actually do have to look at the sign of beta coefficient. So in this case, we know the beta coefficient for body weight is positive. Therefore, this is not the negative value. This is a positive correlation. Okay. So if you go back to lecture note, I put these explanations in your lecture note. So let's check one by one, in case, just to make sure I didn't forget to explain anything. So we go back to this coefficient table, right? So this 0.044 is a value right next to body weight. So this is a slope. So you plug this value in this formula, okay, here. And then the value next to constant is intercept. So you put this value in here. So that's how you construct this equation, okay? And we assess whether this slope, effective body weight, is statistically different from 0 or not. In this case, we rejected null hypothesis and concluded there is statistical association between body weight and plasma volume. Okay, and you can also use this formula to predict plasma volume of future patients whose body weight is 64 kilograms. And to do that, you just plug 64 into this formula. And 2.9 is estimated plasma volume for your future patient whose body weight is 64 kilograms. Okay, and we talked about this, and let's move on. We did talk about this too. Okay. Okay, and we did talk about confidence interval. Right. So let's move on, and so let's play with a graph. And this analysis regression option does not actually give you a graph. Okay, if you do regression linear, it doesn't give you a graph. How can we get the graph? To get the graph, you have to go to Graph and Chart Builder. And scatter plot is what we need. So you click scatter plots, and we don't have a grouping variable. So just grab this one and put it in here. Right? And plasma volume, put it in y-axis, and weight, you put it in x-axis. And then you just click OK. Right? So that's how you do scatter plots. And it doesn't give you regression line yet. And to get the regression line, you double click on this graph, okay? And then here, these options give you regression line. So let's click on that. Okay. All right, so make sure you have a linear, right? And then if you want to have a confidence interval, click mean button under confidence interval, and then apply. So this gives you a confidence interval. And let's see what happens if you put individual button and then apply. So that will make confidence interval much wider. And then because these options provide confidence interval for predicted value of plasma volume. So if you remember, the predictions include intercept and beta coefficient slope, intercept and slope. And these options, and we are putting confidence interval only for slope. Therefore, the predictions include more variation because you have to take into account variation of intercept, variation of slope. Therefore, prediction interval is much wider than mean interval, right? So typically when you want to assess there is association between body weight and plasma volume, and you only want to put the confidence interval for beta, for effect of body weight, which is a slope. You don't have to worry about intercept. So make sure you click this option, right? So let's go. This is a model diagnosis. We diagnose so that we check whether the assumption of linear regression is being met. So these three are the assumptions for linear regression. First, normality. Residuals follow a normal distribution with the mean of 0. Okay, so let's remember what was assumption for t-test. And t-test is distribution of outcome variable, and we want to make sure that is normally distributed. Okay, and we look at it within each group. So here we don't say normality of outcome variable, we say normality of residuals. What does it mean? So you need to look at distance between each observation to regression line, and then this value have to be normally distributed. What do you think? Yeah, it looks okay if you compare this value, that value. If you draw distribution of this value, all of these value, and that seems okay to me. But there is a way you can diagnose normality based on residuals, and I'll show you how to do that later. Okay, so the next one, equality of variances. So this is similar when we check variance of the outcome variable within each group when you do t-test. Okay? And equality of variance means, okay, and if you consider normal distribution of residuals for lower body weight value or middle body weight value or higher body weight value, and variation of these residuals have to be very similar. It shouldn't be changing by body weight. Okay, so I will show you example. And the last one is independence. So when you do linear regression, you need to make sure each data points are independent. So let's go to SPSS and data set. And a quick way to examine independence is to just eyeball your data. So if your data set contains more than one line coming from a single patient, that is a violation of independence. So in this case, you know each line, observation on each line are coming from a single patient. This patient different from this patient different from this patient. These patients are all different individuals. So we know independence assumption is being met. So let's talk about model diagnosis of linear regression. And when we diagnose model and we check whether the assumption of linear regression is being met or not. And here is a list of 4 assumptions. 1, linearity, because we say this is a linear regression, so association between exposure and outcome must be linear. Okay? And normality. When we talk about normality in t-test, and we check normality in outcome variable within each group. And then here, linear regression, and instead of checking outcome, we check residuals. So whether the residuals are normally distributed or not is important. And what is residual? Residual is distance from each observation to regression line. Okay? So if you draw a histogram of this residual in your head, do you think it's normally distributed? I would say yes. Okay, so outcome can be heavily skewed, very skewed, but if the residuals are normally distributed, it is okay. Right? And number 3, equality of variances. So if you check, again, the variances of residuals. Okay, so if you see distance between each observation to regression line, and let's think of variations. Do you think variations of this distance is similar when you look at lower body weight range or middle body weight range or high body weight range? Then we can say that variance seems equal across the body weight. Okay? And number 4, independence. The value of the residual for given case is independent of the values of the variables in the model and of the values of the error terms for other cases. I think I made it too complex. What this means is each observations in the analysis are coming from different patient. So a quick way to check this is go to data sheet. And then if you can say data on each line is coming from different patient, then you can say independent assumption is met. If you have more than one line, let's say if these 2 lines are coming from the same patient, then you cannot, you have a violation of independent assumption. Okay. So, using next slide, and let's talk more on how to check normality and equality of variances and linearity of the association. So let's look at the first graph. So this graph shows the scatter plot of x and y. And if you fit the linear line on this graph, you might put line here. Okay? And then now you focus on the residuals, distance between each observation to regression line. Right? Do you think it's normally distributed around linear line? Then you can say normality assumption is being met. And also, say, if you think about variances, and the variance seems similar for any level of independent variable, then you can say, yes, variances seems equal across the value of independent variable. So we can say, so assumption, normality of assumption is being met. Equality of variance, which is homoscedasticity, is being met. Okay, so that is okay. So let's move on. How about this one? And if you have a data looks like this, you might put nonlinear line. Okay, and when you put the nonlinear line, you have you no longer have a linear regression. So you need to call this nonlinear regression. Okay, and then when you have nonlinear regression, and we also need to check whether the residuals are normally distributed. In this case, it seems yes. And how about equality of variances? Variance of residual seems similar across the value of independent variable. When you look at here, 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 it seems similar. So we can say equality of variance assumption is being met. And although this is not linear regression, so you can't really call this as a linear regression. And then let's say, let's go to move on to the next one. And next one, and if you draw the regression line, you can put the straight line. So you can say it's linear. Although when you look at residuals, what do you think? Do you think it's normally distributed? Yes, it seems normal, although variance seems getting bigger as value of independent variable become larger. So we have to say there is a violation of equality of variance. So variance seems heteroscedastic, right? So it's not good. And then last one, and you might see there is nonlinear association, and then also variances seems getting larger as x increases. So then equality of variance assumption is not being met. So this is no good. So in order to have a proper linear regression, and you expect this form of data. Okay. Right. So let's use SPSS to diagnose these assumptions. Right. And to do that, we are going to use different data set called the Poisson.SAV. And as body weight data have only few data points, so it's really hard to use it for this example. So let's use new data set. Poisson here. Okay. So in this data set, and we are going to examine effect of arterial pH on plasma glycolate. So plasma glycolate is dependent variable. Arterial pH is independent variable. Okay. So you go to regression and linear and put the plasma glycolate as dependent, and then arterial pH in independent. Okay, click on statistics. We want confidence interval, right? And so here is a key point, and here you can. So this button, this box, give you options to do model diagnosis. So you click on plots, okay, and then in here, when you click histogram, normal probability plot, and you can examine normality of residuals. Okay, and then when you put the value here, this will create variables here. This will create plot, and you can diagnose whether the variances are changing across the level of independent variable. Okay, so to do that, in this box, you can put anything which is ended with rigid. Okay, so it can be this, it can be this, it can be this, it can be this. For simplicity, and I just pick this one, Z rigid. Okay, in this box you can put anything ending with predictive value. Okay, it can be this, it can be this. Let's put this one. All right, and then click continue and OK. Okay, so this is a histogram of residuals. What do you think? It's probably hard to judge if this is normally distributed or not because data points are few. We have only 18 samples. But what is important is you see the symmetricities, if this histogram seems symmetric or not. It's not really skewed, so I would say if you increase sample size, you probably have normal distribution. So I feel good about this graph. And there is actually better graph checking normality, which is called PP plot. In this PP plot, if you have a data points lining on the diagonal line, if you don't see any pattern being off diagonal, and you may say residuals seems normally distributed. Okay, this looks okay to me. All right, so the last table, this table is created by you specifying Z rigid under Y box and Z pred under X box. Okay, so what this graph shows is you are looking no pattern in this graph. So if you see the data points are increasing or decreasing, some patterns, and then you violate equality of variance assumptions. So what you expect in this graph is, let's go back to lecture note. Okay, along the line of 0, okay, and you want to see data points are scattered randomly. When you see that, and then you can say variance seems equal along the level of independent variable. Okay. And this is a predicted value, but this model only has body weight, so you can say you can view this as a similar to body weight value. Okay. And then here you can see the standardized residual, And what is good about using standardized residual instead of actual residuals are you standardize residual using standard deviation. Therefore, if the data are normally distributed and you expect 95% of data point falling within plus minus 2 range. So when you see data point outside of that, and that indicate outliers. Okay. Right. So here I have a slide and including showing a choices you can put under Y box and under X box in this SPSS box dialog box. Okay. So this is the final slide. So this is the recommendation what to do when you see assumptions are violated. So you don't see normality in residuals and the variance seems changing across the level of independent variable. Okay. And so this is the list of recommendation by Kakut and Starn. 1. Check for mistakes in data coding or data entry which have led to outlying or influential observations. 2. Sensitivity analysis which examine whether conclusions change if influential observations are omitted. 3. Use of transformations. 4. Explanation of nonlinear relationship between the outcome and exposure variable. 5. Use of methods such as bootstrapping to derive confidence interval independently of assumptions made in the model about the distribution of the outcome variable. So we will talk about this in the next lecture. Okay. And next lecture of transforming variables in linear regression.